I just clicked through in mystery box. And the problem is I forgot what that something was between last year and this year. So that's the nice thing about the mystery box in the slides, though, because it can be whatever I want it to be. So mystery box today, this limited run engagement is how do buffer overflows work? Woo! Yay! No? Not digging on it? I didn't hear wild applause. All right, so mystery box, buffer overflows. I have an example which I wrote over lunch. It's probably not in this one. Where is it? Not this one. So in my modified version of the code, you don't have to pull it up, but here's where it is. There's something called basic buffer overflow. Oh, yeah. All right, so our basic buffer overflow. In this buffer overflow, well, in this program, there is a program. It's using string to unsigned long. This is the equivalent of A2I, which we saw before, except it's an unsigned output. So whereas A2I, if you give it something with a 1 in the upper bit, right, it's going to get confused because it only wants the A2I one for negative values. It doesn't like them. So string to unsigned long says I'm going to give argv of 1. So I'm going to give some number as the first input parameter. And, I'm going to give it as a string, obviously, on the command line. And then that string to unsigned long is going to convert that into an actual number, a 32-bit value size, right? So I give a size, and I give a value. So size and value on the command line. And now I'm going to take size and value, and I'm going to pass them into lame. Lame is a subroutine. Now, we check if the return result from lame is 0, not 0 is true. So if lame is not true, print, well, call awesome, right? So if this is not lame, we will call awesome. Otherwise, we will print out, I'm so lame, in the sad face. Okay? So let's see under what condition this is not lame. All right, well, we take size, let's see, we got size, we got value, we got array 1, array 2, set that value to that, and we memcopy, and, oh, we always return 1. So this is always lame. So therefore, when I run this program, it will always print out, I am so lame. There's main. Let's see if I have any parameters there already. If I do, then you need to close your eyes momentarily. Okay, good. So I need some parameters. All right, 1, 2. Don't know what the parameters are going to be yet. Pass in 1, 2. Oh, why are you dying? It's got to be hex. X2. So this string to unsigned long, it's saying treat the second number as a base 16 number. So I have to put 0x to say it's going to be 16. Try that again. That sucks. Why is it dying on that? I'm so lame. I don't think that's going to make a difference. Oh, well, this is release, and that's like a terrible idea. Wait, does it have to be optimized? I think that's right. Well, let's see. I am so lame. Can't even get my own example to work. That makes no sense to me. To the disassembly. Well, the thing which strikes me right here is, I'm doing a call, but I'm not like cleaning up the parameters to the call. So I'm wondering if I like screwed with this and set it to standard call or something like that.
Hey
Yep.
Zeno, this is Greg. When I built it, I was getting warnings about string to unsigned long being undefined, so it's assuming that it returns an int.
Uh-huh.
So I
Well,
don't know if you're getting the same warnings, or if you have to include something
good
else.
question. That could be it. Let's try rebuilding it. Yeah, so string to unsigned long is being considered undefined.
I need, I think, a STD lib as well.
Standard lib as well? Ah, compiled everything. Built just that. Well, now it's saying I have it, but it has like a different definition. But that may be good enough. So let's see here. Nope. All right, we're going to come back to this. I have no idea what changed. All right. Now we have to go back to lecturing, and this is going to be such a disappointment compared to seeing the buffer overflow example. All right. Soldier on. So, messing with a disassembler. Whereby messing with, I mean causing a disassembler to actually give you the wrong sort of output. So this is this is talking about an academic paper actually from around 2003. And so this Lin and Debray paper, they were talking about how you can obfuscate an executable so that static disassembly is going to fail on it, basically. So in the paper, they compare and contrast two types of ways that you can disassemble. So there's the obj dump kind of way, where you start at the beginning and you basically go top to bottom and you just disassemble bytes in the order that you see them, subject to some, trying to figure out where functions start. So you see a function, you start, you disassemble top to bottom. On the other hand, there's recursive traversal disassembly, which is what IDA does. So in recursive traversal disassembly, what you would do is you would start at the beginning of the program, you would go along and you would disassemble instructions until you see your first sort of control flow changing instruction. So if I see a call instruction, I go to the target of the call, I disassemble everything there until maybe I see a jump instruction, and then I go to the target of the jump, and so I just keep recursing down. Every time I see a branch, I take that branch. And I go to that target, and I disassemble code at that target. When I eventually see something which, goes back like a return instruction, either I see a return instruction or like maybe it just falls off the end and it's, well, typically you're going to see a return instruction. But when I see something that indicates this thing is done disassembling over here, for instance, let's say you have, a blob of code here. This is your first chunk of code. And, this has like a, jump to code 2. Code 2. Wow, it's terrible. Jump to code 2, right? And so that may tell you that we're going to go down here, and you know this is code 2. Right, and it's going to go along and disassemble this. And so where this may stop, it may stop in that there may be like a jump to up here, and then this disassembles until like this hits something where you've already disassembled, right? And so if you start disassembling here, you get to here and you say, well, I already disassembled this in code 1, then this descent is done, and you go back up a level, and you go back down here, and then you start disassembling right here, right? So basically the point is you just, every time you see something which is targeting somewhere else, you go to that target until you get to some termination condition, whether it's a return instruction or like you've hit some code that you've already disassembled, and then you recurse back out. Yes?
So when you say some code that you've already disassembled, couldn't I potentially, albeit it's probably headache-inducing, offset by a byte or two and jump to something which, when you start a couple of bytes offset, gives you a completely different interpretation of that code we've already disassembled?
Yes, you could do that, but what the disassembler will basically do is it'll go with, typically, I mean, they can do it one way or the other, but whatever way the disassembler chooses to do it, right? So she said, what if, you know, I jump from here into there, for instance, or well, I went from there and then maybe I went down to, you know, here or something like that. Wherever you go, if you try to target into some code which the disassembler has already disassembled, they can either say, no, I will not print my new interpretation of that code, because this is just flat disassembly now. This is not like running a debugger. This is just, I'm going to give you a list of what I think the instructions are. So it can either say A, no, I consider that an invalid target, and it'll just print out the first interpretation. Or B, it can say, yes, I consider that a valid target, and then it'll print out that interpretation of the overlapped thing. And so therefore, this could then be some different code, and there could be like some region of ambiguity in there where like, you know, this first instruction got cut in half, right? And therefore, it maybe needs to back that out and say, well, I don't consider that a full instruction anymore. I consider that 2 data bytes, and then the subsequent interpretation. So it's really just disassembler can decide how it wants to do it. It can either choose to allow the overwriting of its first notion of code, or it can say, no, I will never overwrite my first notion of code. All right. And so, you know, this paper also talked about sort of this, quote, self-repairing notion of x86 assembly. So when we saw that offsetting the bytes by a couple of bytes each time, we got a slightly different description of the disassembly. But eventually it would sync back up, right? When we were in GDB, eventually we would get like this, we would get that pop EBP, or when we saw everything like so, right? Even if I offset by some number of bytes, eventually the stuff seems to always sync back up at this call instruction, or, you know, somewhere else later on we get back to the original interpretation. So this Lynn and DeBray paper sort of recognized that fact that while you may be able to like get a disassembler to start disassembly at the wrong location, right? So let's say you tricked the disassembler into disassembling start at, you know, 386 rather than 385, right? And you got it to print this sequence out. The thing is, you would have only screwed up the disassembler for 3 instructions here, right? So if the human's looking through there, the human may have been like, saw that junk, and, you know, he may have thought something wrong. But eventually, it's going to self-synchronize again, and it's going to get back to the correct thing. So just messing with it one time does not guarantee like everything's messed up. It just kind of says for some small area after that, potentially there's the ability, potentially the disassembly is going to be messed up, but it may eventually become fixed again. So that has no guarantee that if the analyst is looking at the code somewhere else, that region somewhere else may not be screwed up. So there was a number of different types of things that they said, here's things we can do to modify our assembly in order to make it so that different disassemblers kind of choke on it and give the wrong output. So in the case of the linear sweep type things, so this was recursive descent traversal, right? Recursive traversal. In the case of linear sweep, there's a very simple sort of thing you can do. If the code is going down, so I said that, linear sweep, it's going to assume here's one instruction, then here's the next instruction, then here's the next instruction. And so if we have something like, this one sucks. Oh, that's why why my fingers are all dirty. So let's say I have push EAX, and then call, blah. And then, we assume that, so here's the thing, a linear disassembler assumes that one path here is to call blah, and then it assumes that the blah is going to return immediately to the instruction after call, right? Because call pushes the address of the instruction after call. So obviously the code that's going to be well behaved is always going to return to the instruction immediately after call. So it's going to take the byte immediately after call, and it's going to disassemble it, and maybe it's going to get add ESP or something like that, right? So that's kind of how linear traversal says. It says when I have somewhere where control flow diverges, I will assume that I will do this first, and then later on, I'll maybe go back and find out where the call is, and maybe I'll disassemble that if I didn't disassemble it otherwise. Probably not, actually, since this is linear. Right, it just goes top to bottom, and if blah isn't in our code, then, oh well. If blah is in our code, well, then presumably it should get hit eventually because we're trying to disassemble all the bytes in our code. So an example of something you can do, well, that's one example. And then, another example may be something like this. Compare, what was it, EDI and 3. We saw that earlier, right? Jump below target, right? And then if this jump doesn't, if this condition below doesn't hold, then we fall through to the next instruction, right? I don't know. So here's the other thing, right? So linear top to bottom thing is going to say, well, yes, I'm going to always, disassemble the next byte after the conditional thing because either it's going to go to the condition or it's going to fall through, and the next byte immediately after a conditional jump should always still be valid because it's going to go one way or the other. There is the possibility that it's going to fall through, and therefore this has to be a valid instruction at the end. So, what is the literally unconditional jump? Yeah. Okay. And then a third form. Right, so I don't know what EBX is here, but, so we may have an unconditional jump, but again, the thing is, this is definitely going somewhere else, right? You have no reason to believe that the next byte is necessarily an instruction, but in practice, right, all these instructions get put next to each other. So probably, unless this is the end of file, there's probably another instruction here, and maybe this thing jumps down, but maybe it was like that for loop, right? So maybe you jumped down somewhere, and then you jump back up somewhere else. So the linear disassembler doesn't care. It just goes top to bottom and says whatever's coming next, I'm going to put an instruction. I'm going to treat that like an instruction and write that out. So whatever that will be, we'll say push whatever it is. Okay, so here's how you can mess with objdump moving down. So, and I'll say that generally speaking, these sort of obfuscations are assumed to take place post legitimate compile. So you have some binary, you've compiled a binary, you've disassembled that binary, and you want to now obfuscate it. So you've got a binary which disassembles correctly, and you want to make it disassemble incorrectly. So what you do is you pull apart your binary, potentially, instruction by instruction, and you find places where you have control flow changes. And you know that no matter what, the linear descent disassembler is always going to assume that the next byte sequence immediately following some control flow change can still potentially be legitimate. So what you do is you slice this apart, you pull apart these instructions. Let's make it something like this one right here, right? This is a good example where, yeah, you can see it's a call instruction. Probably the next instruction is going to be legitimate. Well, so there's a couple of ways you could do this. One, you could modify blah so that blah doesn't return directly to the thing which was pushed. It could like take that address and then like add 4 to it or something. And then it could actually return, when this blah returns, it could actually return to right here. And so then these 4 bytes would never actually be executed, right? Call would call somewhere else, and when it returns, it would return to right here. And so these 4 bytes would never be executed. So you could put in whatever you want for bytes right here. And if you put, say, like, you know, so you take it apart and you put it back together where this instruction, the add ESP plus 4, gets put down here. Right? And so then there's this gap right here of 4 bytes. And what you could do is you could put something in here like maybe a 5-byte instruction, right? So you know that I'm going to do an instruction, and this instruction is defined by 5 bytes. So I'll say maybe it's like E8. This is like actually another call, like that's a prefix for a call instruction. You don't need to know that, right? But an E8 plus 4 bytes can be like an offset, like say a 32-bit offset, right? But I can't fit 4 bytes right here, so I'm going to put 3 bytes right here. And remember, these bytes right here are never actually executed. So I'm going to put like, you know, some offset in little endian order. I'll say 1, 2, 3, 4, I don't know, 4, 0, something like that. And so the thing is, when the disassembler comes along, it saw the call instruction, it disassembles the call instruction. It gets to the next byte immediately after the call instruction, and it assumes that that byte is something which can actually be executed. But there's nothing to say just to a disassembler that byte will ever get executed. I can modify things so that it never gets executed as an instruction. Disassembler doesn't know that. It says, aha, E8, that's a call instruction. Now I will take 4 bytes. So it's going to like grab a byte from this next instruction. So it's going to take another 4 bytes right here. One of the bytes, the first byte for that add instruction is going to be, you know, merged into the disassembled output for what this call instruction's address is, right? Because we had a 4-byte address, got to get those 4 bytes from the next 4 bytes. One of those bytes came out here, and then now it's going to start at the next byte after that. And so in the middle of this byte, whatever happens to be, in the middle of this instruction, whatever this byte happens to be, it's going to say, now I'm going to interpret that as some instruction, right? And then I'm going to interpret that as some instruction, right? And these are contiguous instructions, one after another. Right? So, and then it goes down. So by playing this sort of game where you make it so that something immediately after a control flow is not actually ever used, the disassembler doesn't know that. So it always starts right here, starts disassembling. You know, like I said, this can be a 5-byte instruction. It can be a 2-byte instruction, and then, you know, a 3-byte instruction, a 4-byte instruction, well, 3-byte instruction, then a 5-byte instruction, right? And the point is, this may be the legitimate instruction in which you're trying to hide from the analyst, right? So the analyst wants to see push, call, add, right? That's what the original compiled code did. But you pulled the code apart at the instruction level, and you put it back together in a way where there's maybe some junk in between instructions, but you've made sure that that junk never gets executed as an instruction. It's just there so that when a disassembler comes along and hits it, it disassembles it incorrectly. So that was one example where I said, you know, you could pull this apart and you could maybe modify it so that, you know, if you're pulling everything, you know, if you're going to take things apart at the assembly level and put them back together, you can do arbitrary functionality, right? So I could go to blah, and like right before blah does a return or something like that, I could do like add 4 to, you know, EBP plus 4, something like that, right? And that would make that saved EIP be 4 bytes lower so that when I return, you know, it goes to a different location than immediately following the stack. So that's one way. Another way that you can do things is you could take a conditional statement like this, right? And it says jump below, and you could make this functionally unconditional. So you can say, I'm going to put some sort of compare before it where I know what the input parameters are, and I will never, ever not take the jump, right? So the simple example, right, is I could do a jump 0. Right? It says jump if the 0 flag is set. And then I could do like, you know, compare 1, 2, right? So is 1 minus 2, 0? No. This jump 0 will never be taken now, right? So it'll always go this way, and then, well, sorry, that's for screwing up recursive descent things potentially. Jump if not 0, right? So this result will never be 0. This will always take this jump if not 0 kind of thing, right? And therefore, whatever I put here, the disassembler is going to disassemble that, but there's no reason to believe that I will actually ever execute that. So therefore, that can put some instruction stream, and I can then again, you know, put some offset down here so that this junk byte gets grabbing a chunk of some other legitimate byte, which I would have had otherwise. So this is one way that you can mess with the disassembler, essentially. You can force bytes in here. That's going to alter the interpretation of this because no longer is the first byte going to be something which says I'm an add. That first byte is going to get added into this as far as the disassembler is concerned. And then the next byte will be some other instruction. And so the reason why I talked about the multi-byte things is, okay, so I did this, and I screwed it up, and I got it off by 1 or something like that, right? But that's the same thing as we saw before with the GDB. Okay, I got it off by 1, and now this next thing is not going to be an add instruction. It's going to be whatever that first byte of the second byte of the add instruction was. But then eventually this may synchronize again. And so what they talked about was the need to do this over and over again so that you just keep screwing up. You know, you go a couple of instructions, you screw it up again. You go a couple of instructions, you screw it up again. That completely messes up what the analyst sees for disassembly. Now, that's not going to help for actual debugging, something like that, right? So keep in mind the difference between static code, which I'm just looking at on the page, and code which I'm executing. So when I'm in a debugger, the debugger doesn't care about any of that obfuscations, right? The debugger knows that if I go here to the call and if I execute some sequence of instructions, I'm going to come back at, you know, that address plus 4, and I'm going to hit an add, right? So the debugger will see the correct series of instructions, but it'll look like to you, if you're looking at the disassembly, it'll look like you're jumping into the middle of instructions. You're like, no, how can you jump there and have an add? There's some other call instruction there. How are you jumping into the middle of a call instruction and getting an add instruction, right? But once you start seeing that, then it becomes clear pretty quickly, like people are messing with your disassembly. Question? No? Okay. Question?
So how much does the recursive traversal defend against that?
Okay, so how much does the recursive traversal defend against that? You can basically play the exact same sort of game with recursive traversal. So I said here, right, I can make this unconditionally always go to the target, right? Recursive traversal assumes that it's always going to go to the target and it's going to always go to the next thing. What if I made this unconditionally never go to the target? Now I can take this target and point it at the middle of some instruction stream like you were saying before, and then it's really just a question of, does that disassembler allow the pointing in there to overwrite the previous interpretation of code, or does it just say, if you point into code I already disassembled, that's what it is? But then you can play the same game of don't point into code which the disassembler has already disassembled. Point into some blank region, but where you know that's in the middle of something which would have been legitimately disassembled. So get there first, force the disassembler to disassemble something incorrect, so that when it comes back through the legitimate direction, it's going to have the incorrect stuff first, and then it'll say, well, I can't overwrite this incorrect stuff. I've already disassembled it.
Do the recursive disassemblers give the user flags to say, let's try overwriting this time, let's try not overwriting this time?
Well, kind of not. It's not something such that like you just set a flag and you say, well, let's overwrite this time, let's not. It's more like in IDA, if you want, you can go back in manually and you can say like, okay, well, this looks like someone's like jumping into the middle of thing. undefine this instruction. So you could say, undefine this call instruction starting right here, move 4 bytes forward, define an instruction here, and then it would like, so it would undefine the sequence starting here, and then there, and then there, and then there. And it would take like all the sequence following that illegitimate call. It would turn that back into bytes. And you would come in and you would say, start at this +4 address, turn that into code, and then it would turn all that into code as far as it could disassemble it. So that's why, this, to a first approximation, it definitely screws with analysts. And then to a second approximation, you do have the tools to fix it in something like IDA. You can go back through undefined stuff and redefine stuff. It's just then it's still a pain in the ass. So, and I will say, while things don't use necessarily, shall we say, the Linen-Debray way of doing this modification, they do definitely do things like jumping into their own instructions. So you will see plenty of malware which jumps into the middle of instructions, but in reality, that's just them knowing what sequence of bytes they need to actually do. So that's one thing. And then there's a bunch of other things. Well, so opaque predicates is kind of what I've already explained. One of the nastier things that you can do is having a branch function. This is like, let's take all of the branch kind of instructions, all of the control flow variants within our code. So if normally we would get somewhere and we'd have a jump to some place, and that's all very, an unconditional jump, there's always like it comes from one place and it goes to another place. And you may have a bunch of these throughout your code. But instead of doing that, change everything so that everything gets funneled into one box. Right? So everything comes into one box, everything goes out from that box, and now you start losing the correspondence between, this jump at A1, it jumps to B1, right? At A2, it jumps to B2. You lose that because A1 calls to this function, and we'll see why it needs a call in a second. A1 calls to this function, but this function calculates some stuff, and then it goes somewhere, right? And so the question is, how do I know, just based on seeing A1 called into this function, how do I know it didn't go to B5? How do I know it didn't go to B6? I can't just look at it and say, this goes there, right? Whereas I can over here, I can say A1 goes to B1. So when you funnel everything into the same sort of control flow, this kind of like flattens your control flow, and it makes it really hard for an analyst to follow, like this code goes to that code, and then it comes back to that code, right? And so it makes it so they have to kind of calculate what's happening here. And so in practice, how this function f would be implemented is it's kind of like a big switch statement. So if I turned my jump to B1 into a call to f, what would happen is when I do that call, the address after A1 gets put onto the stack, right? So the call instruction will automatically put the address after A1 onto the stack. And then this function will say, read EBP plus 4. That's the address that got pushed by the call. And then have a switch statement. If that address is that address down here in my switch statement, case, 40, blah, blah, blah. If it's that, then go over here to B2, something like that, right? And so that gets very annoying for an analyst quick to like always be funneled into the same place, figure out where we're coming back out, that sort of thing. So this is more like a visualization kind of attack. So, we showed before how IDA will have your nice little, well, this won't be exactly accurate, but what is it? I think it's actually the second one. Right? So I said, when you graduate to IDA, you get nice control flow graphs like this, right? And okay, this is a conditional jump goes here versus there, and this conditional jump goes there versus there. What if like all of these just like all funneled into one place, and then they all split out to all the other paths, right? That would be, harder to look at, and the bigger the graph was before you did this thing, the harder it is and the more annoying it is. And so, let's see. And then there's a thing with obfuscating jump tables, but I'm going to skip that because I don't remember that very well. Oh, I think that was just putting in sort of fake jump tables. So under the assumption that a jump table maybe looks like we have some base address and we're going to offset somewhere within it. Like, well, under the assumption that a switch statement turns into this sort of jump table where you have a base and you switch based on your cases, you go down there and then that tells you where you're going to go. You can put in sort of fake jump tables where the disassembler potentially, if it's jump table aware, it may be trying to create this sort of thing and it'll say, it looks like, case n is here and case n plus 1 is there and case n plus 2 is there. And I see that it looks like you have approximately 40 cases. Well, you can kind of put in like fake cases there. You may not have 40 cases, but you trick the disassembler into making you think you have that. And then it like takes this big blob of thing and puts a fake jump table in there. So let's see. One thing I'd like to say here is that there was then counter work, right, in the academic community that says, okay, we have these better algorithms for how you should actually go about doing disassembly to counter these sort of attacks, right? But, I asked the authors of this counter attack paper, or counter disassembly algorithm paper, if anyone was actually using their method to get around these sort of things, and they said not as far as they're aware. So you can think of things like IDA and objdump and other things are still vulnerable to this sort of messing around with. And then the one other thing I would point out that I don't have in my slides here is I've actually seen, so this, this work was done in 2003. It seems there's been some parallel development of this by someone else who did not give credit to the authors because maybe he developed it on his own, but I won't judge whether or not that's the case. All I will do is show you that we have something very similar where you can download it, apply it to executables, and do this sort of obfuscation to really give an analyst a bad day. So rnmicrosoft.net, actually, right? This is Nick Harbour. He works for Mandiant. Gives plenty of talks. And he's got this tool here called P-Scrambler. And that has to do with like obfuscation. And so it pulls things apart, puts them back together in obfuscated forms. Oh, and so I think what I didn't talk about here, for instance, was another thing that you can do things like you can make, so one way you can really mess with things in order to do like lots of these sort of unconditional things where you've got junk down here. If you think of like that you had some sequence of 3 instructions or something like this, say you have a sequence of instructions that have no control flow in them at all. You got like move, 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 add, move, 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 push, add, move. All right, you can take all those and you can say, okay, well I want 3 of those instructions and then another 3 of those instructions, and I'm going to separate them and I'm going to mix up their order, but I'm going to put a jump from the end of the first one to the beginning of the second one so that the ordering is still maintained, but so let's do like push, push, move, add, and XOR, move, whatever. Right? So let's say I'm again, splitting up this binary and pulling it apart and putting it back together. I'm going to like take this chunk of assembly instructions. I'm going to take this chunk of assembly instructions. And I know that these need to be executed in this order because that was my original unobfuscated binary. But, and then I may have another chunk here. So we'll call this chunk 1, 2, and 3. Right? I take these apart. And now I may order them like 3. Well, I don't want 3, 1, 2 because then they're still in order. So I can go with like 2, 1, 3, right? And what I can do is I can put at the end of the 1, I could put, in the simple case, if I just wanted to do something, I could do, jump to the beginning of 2, right? And so this would go like that, right? And then at the end of 2, I would have jump to 3, right? And then that would go like that. Right? And so this will also mess with the analyst, right? Because you'll have all these jumps all over the place. The bigger it is, the more jumps, right? You can bring this down to the granularity of 1 instruction if you want. 1 instruction at a time, split up by jump instructions. Now let's make this nasty, right? So just jump instructions, that's not nasty enough. Let's make these those unconditional, conditional jump instructions and let's put junk in between these blocks. So instead now, I'm going to have what looks like this. So 2 with like a J and Z, which will like always be taken, and then junk, and then 1, right, with like a JBE, which will always be taken. Well, JBE to 2 and J and Z to 3, and some junk, and then do 3, and 3 goes wherever 3 goes, right? So now, by having only a couple of instructions at a time, and I say that, you know, this junk adding method can probably screw up the next couple of instructions, I'm making the control flow horrible to follow. I'm making the next, like an entire block potentially at a time is all screwed up, and like that's not the real instruction sequence that is actually going to be executed. And then at the end of the day, the analyst has to figure out how to put it all together and figure out what was that little snippet of code trying to do, right? He has to ignore all of the rest of this goings on, has to be redefining his instructions as he goes along, and then he has to say, oh, I was just doing a few pushes and adds. And so this P scrambler does that. I can't remember if it does the actual junk insertion or not, but it definitely does the spaghetti codification of slicing it up, reordering it, putting control flow between. Yes?
I'm curious, how much do antiviruses are they able to detect this type of stuff? So I can see, like, you see a piece of code normally shouldn't have, 10 million jumps. So
well, it depends, right? So you say, so where would the, what is a safe heuristic for the antivirus to use in that case, right? What does the antivirus have to say? You may not have less than 3 instructions before jumps. Like, how does the antivirus actually codify that as a heuristic where I can't just step back one, right? So if they say you can have, not less than 3 jumps or 3 instructions and then a jump and then another jump, things like that. So we as humans may be able to like pattern recognize this and stuff like that, but think like someone having to write an antivirus program. How do I write the logic sufficiently descriptive such that I don't cause false positives on real programs, right? Remember that for loop? That for loop had like 2 jumps and a conditional jump all within the space of like, 7 instructions or something like that, right? Why do we not flag on that and we do flag on this, right? So absolutely, you could think of there being some way to generate some sort of heuristic for this, but I'm not aware of anyone trying to do that sort of thing. And secondly, it's probably harder than it seems to actually codify in a way where you don't get false positives. Right? People aren't going to tolerate false positives for a heuristic like this. They say, why are you flagging my stuff as viruses just because I have, some tight sequence of jumps or something like that? And then, would it flag it as junk-based? Well, would the AV flag it as malicious just because it does this jump obfuscation or something like that? Okay, well then your AV now has to have a disassembler built into it as well. And if there's one thing we know from IDA, it's that, disassemblers can be large and complex. I mean, granted, IDA does a bunch of other formats as well, a bunch of other architectures and things like that, but you don't want to start adding in a disassembler. Although I say that, and they probably have some basic level of disassembler anyways, because I've heard that they do like emulation of the first X instructions. So I don't know, but I would caution that that's probably harder than it seems. So, and then I just want to bring up his slides from DEF CON 16, 2008, 5 years after the Lynn Debray paper. I should be nice. This is going on the internet. No trolling. Okay, so basic form of like packing. So he was comparing this sort of obfuscation to your typical obfuscation where you like pack something with just a regular packer. All right, so here's something interesting, right? Let's take the original call tree and, turn it into this dispatcher, right? Let's funnel all of this control flow into a central point and out to whatever the targets are. And that makes it very hard to like analyze what input corresponds to what output, right? Because A does never A never corresponds to E, right? But you don't know that based on looking at this thing, right? For all you know, A can go to anything. But in reality, A can only go to C or B. So there's that. And then, let's see. I feel like there's definitely something talking about the obfuscation of adding junk code and stuff like that. But at least, yeah, so here he talks about code chunking. So this is the notion of, let's just take some sequence, break it up into some number of assembly instructions, and put unconditional control flow between them, right? So whether the unconditional is just a jump instruction or it's an unconditional conditional jump instruction, right? One way or the other, one always has to go to 2. Right? One always goes to the beginning of 2 because in the original code, you always went 1 to 2. So this is what's happening, and like I said, this binary is available online. So you can go and do this to an executable and then tell the people to analyze it. Actually, I feel like in the last class I downloaded it and actually showed like hello world and you see all the jumps and stuff, but I'll leave that to you if you want to go play with P Scrambler. There we go. So he's saying take an unconditional jump and turn it into a test EAX, right? So testing anything with itself, ending something with itself, right? As long as EAX is 0, then it's always going to set the 0 flag. Otherwise, it's not. So he's basically assuming right now this call is always going to return 0, and therefore 0 and 0 is going to be 0, and then you would do that jump, basically. Oh, sorry. Except he's not assuming that jump's going to take place. So I guess he's assuming it's not going to return 0. Anyways, that's again just the example of making unconditional conditional control flow. All right. So, let's see what else is in there. There we go. There's the junk thing, right? Got conditional control flow, but you did XOR EAX with EAX. The result is definitely always 0 for that. So go ahead and feel free to put a junk bytes in the middle, and then, you know, you're jumping over the junk because you're always taking the branch. Alrighty. That's all I'm going to say about that. Feel free to go look at it yourself, and you can run it on real things. Okay, so we're going to talk about the lab, the end of the day lab, and then we'll take a break. You know, take a break at your leisure after this. We'll get us started here, and then you can take breaks as much as you want, end whenever you want, leave if you want. Don't care. But I'm leaving at 5 because I have a flight to catch. Maybe 5:30. All right. So, binary bomb lab. Like I said, by default, unless you have a good reason to do otherwise, you tell me so after we start. You should assume you'll be doing this in GCC in your Linux VM. All right, once you get the bomb, you tar xvf bomb.tar. That will give you just a single binary bomb. All right. And if you then just do /bomb to run it, you will be prompted for some input. I'm just wandering around to check people's things. All right, you got it running. Good. All right, so it's prompting you for input. Go ahead and give it any input you want, because only certain input will cause it not to explode. And your job is to figure out what the input should be to make it not explode. So I will help you with the first phase, which is extremely much simpler than the second phase. So the first phase will be nice and easy. The second phase will be hard, and you will be frustrated. But it's okay, because it's reverse engineering. Expect to be frustrated. All right, so I'm going to put in some input. Input. Boom. Failure. That is not the input it is looking for. So it's time to bust open GDB. All right. get your command file from wherever it is. I don't know where mine is at the moment. Mine's going to be somewhere on desktop, wherever. Copy, desktop. All right, I'm just going to put mine in my local directory. All right, so gdb -x in your command file, and then /bomb or bomb. Right, so we're going to start up bomb in GDB. We're going to have all of our breakpoints set at main, all this good stuff, right? And so, well, okay, sorry. I'm going to back up a step. So frequently, right, what you might do, maybe the first thing you're going to do is like run objdump on it because you want to get like a high-level perspective on what's going to go on. So I'm going to do objdump-d to disassemble it. Bomb. All right, so we've got init, right? I'm going to go try to find a main. In less, if you use slash and then main and greater than sign, that'll slash is for search, and then main and greater than sign is just because we can see these greater than signs around names of stuff. So I'm going to search for that. I'm going to go find main, right? So again, slash main greater than sign, press return, and you will find the beginning of main. And so now I can start sort of looking at a high-level overview of what's going on in main. So just to a first approximation, so this is again where I'm hoping the reverse engineering class will help you with this sort of notion. So when you start out with something that you're just trying to reverse engineer, you know nothing about it necessarily, I think that one of the most useful things is to focus on the control flow kind of stuff, right? That's why we have control flow graphs. And in terms of this right now, you could look at all the jumps and stuff like that, but let's go even higher level than that. What are all the calls that are going to occur, right? So which functions are going to be called? Now, this is nice to you in that it has debug symbols, so you can find out the names of the calls. But, okay, the first thing I see is fopen. All right, that means nothing to me. Then I see printf. Okay, well, I do know that it's going to print something out. Then I see exit, then I see printf, then I see exit, then I see initialize bomb. Okay, that's interesting finally. Initialize bomb is probably more or less where I want to start, but you know, let's keep seeing what's here. All right, then I see a printf, read line. Okay, phase 1, and then phase 1 diffused. Keep going, printf, read line, phase 2 diffused. All right. So as it said when it printed out at the very beginning, it said you have 6 phases in which to blow yourself up. You start at phase 1. Phase 1 wants you to input a certain string. If you put the right string, you successfully return from phase 1, and it calls phase 1 diffused. Then you continue along. It's going to print out, you know, something, and then it's going to it's going to use read line again to ask you for your input. And then you get to phase 2. It wanted some specific input for phase 2. If you succeed, you will return. You will go to phase 2 diffused. Well, just the generic phase diffused. And then continue, right? So there are 6 phases, and there is a secret phase if you give the right input. So again, the people who are trying it on hard, you get to look for the secret input. And so basically, you just need to keep giving the right input in order to proceed from one phase to the next until you finally get to the end and it says, oh, you've diffused the bomb, good job, whatever. So that's our first high-level overview. We can see the stuff is named conveniently, phase 1, phase 2, phase 3, etc. Phase 6, and then after phase 6, eventually it returns. So notice that we never saw like a phase 7 or a hidden phase or anything like that right there. I think there may be something called hidden phase. No? Well, I can't just search for 7, so find the hidden phase. All right. That's our high-level assembly overview. Looks like it's a sequence of phases. Got to give the right input in order to get to the next phase. So objdump is one way you might do it. Now we know it wants some string for an input. So let's go ahead and use the strings command to dump out every string in there because maybe it's comparing my input versus some hard-coded string in order to figure out what it wants as an input, right? So you as the naive architecture student are going to run strings on it and try to find all those 6 strings that you need to input. All right, so I piped that into less. Okay, well, I got the names for my functions. That's fine. Function names, glibc. Okay, here's my little, you have 6 phases in which to blow yourself up. That's what it printed. Okay. Phase 1 diffused, that's what it'll print next. Phase 2, phase 3. Okay, so these are probably the strings that it prints out after each time. And then good work on to the next. Public speaking is very easy. That's interesting. %D, %C, %D. Giants. Wow, you've diffused the secret stage. We got some strings for CMU machines. What was that? So you think you can stop the bomb with Control-C, do you? Okay. Oh, there's an email kind of looking thing. We got a subject. Okay, we got diffused, exploded, send mail, error, boom, the bomb is blown up, etc. I have no idea what that is. Congratulations, you've diffused a bomb. So, all right, one of those strings maybe was one of the strings which you need for input into the binary. But let's not just brute force it and try all of those strings, shall we? Let's try to use our nascent reverse engineering skills here. So back into GDB. We got a breakpoint at main. Let's go ahead and just run. All right, so here we are in main at the beginning. I'm going to use x/10i to see the next 10 instructions. And then I can just keep hitting return, and it'll keep doing the previous instruction that I told it. So it'll do another 10, and then another 10, another 10. So I saw earlier that there's this initialize bomb phase, and then there's this phase 1. I probably want to go set a breakpoint on phase 1, right? So I just want to get straight to phase 1, and then let's do this thing. So I grab the address in front of the phase 1. I copy that. I do break, star, and then the address of phase 1. So I did that. Then I'm going to hit continue, or C, to run until I hit my next breakpoint. Okay, between me and the breakpoint is this request for input string, right? So I need to give some input. I'm going to give something that I know this is my string, so I can try to see if I can find my string in memory, right? So again, I'm going to just put in input. All right. So I put in my input. My string is now somewhere in memory. I don't know where at the moment. Now I'm going to call into phase 1, and I'm going to try to see what's it going to do. I'm going to try to identify where my string gets used in phase 1, and then I'm going to try to identify what it gets compared to potentially, right? So, right, my string is probably going to be compared against some other string, because otherwise, how do they know that I gave the right input or not? All right. So I'm going to step into phase 1 using the SI or step I instruction. So I'm now in phase 1. All right. What do I got? Standard function prolog. All right. So it's going to set up a stack frame. Subtract 8 from ESP. So it's going to allocate some space for some local variables. All right. Move EBP plus 8 into EAX. What do we know about EBP plus something? Matt?
It's being passed into it.
That's right. EBP plus something is stuff that's being passed in. And what do we know specifically about EBP plus 8?
It's the last thing that was pushed on the stack before the previous.
Right. So it's the last thing which was pushed on the stack, and since the stack pushes occur in order from right to left, it's the first parameter of the function, right? So talking from left to right, which is what we normally think of. But all right, so that's the first parameter passed into phase 1. We don't know what it is, but let's step until we see that moved into EAX, and then let's just look at it. So step by, step by. This is very annoying for me. I mean, I hope you have your screen small enough that you don't have this split in between each time. So your text should be small, and you should be able to see all your window all at once. But all right, step by. And then, okay, now we're going to move the first parameter passed into phase 1 into EAX. So right now, before that, EAX is just some 804 whatever. After that, okay, EAX is now 804B680. All right, what does that mean to us? Does that mean anything to us right now? Amy, can we say anything about this value? What do we know, if anything, about this value?
It's like, program address.
Yes. So it looks roughly like it's going to be in the main, it looks like it's kind of an address in the code, right? So we see the rest of our code is somewhere in the 8048, blah, blah, blah. This is an address which is 804B. So, okay, it may be something plus a lot, but it's still roughly in the same area, right? 8 plus, 3B. So it's, hex 3000 greater, but it's still roughly in the same range. All right, so looks like something maybe in the code. All right, now we're going to do add FFFFF8 to ESP. So what is this actually doing? Katie, what do you think this add FFFFF8 to ESP, how is ESP going to change here? So if, for instance, my ESP is ending in 3D0, what do we think ESP is going to be after this instruction? So 3D8. Well, if I add the 0 and 8, yes, that gives me 8. And then if I add the F and the D, what's that going to give me? Well, let me just put it a different way, actually. Whatever that's going to give you, you're going to carry the 1. And whatever F and 3 is going to give you, you're going to carry the 1. And whatever F and F is going to give you, you're going to carry the 1. And you're just going to keep carrying stuff, and you're going to, like, overflow, and you're going to have too much. So when all the overflowing and stuff is said and done, the alternate interpretation of this FFFFF8 is negative 8. So it's actually like FFFFF, which is negative 1, minus 8. Well, let's see. Hold on a second. Make sure I'm doing this right. Yes. FFFF is negative 1, E, blah, 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 and you go down. So I think this is negative 8, basically, because if you added 8 to this, you would get 0, right? So negative 8 plus 0. Negative 8 plus 8 is 0, right? So if I took this and I added 8 to it, so if I think this is negative 8 and I added 8 to it, the 8 plus 8 would be 0, carry the 1, and all that would like stream out to being all zeros, right? So negative 8 plus 8 equals 0. What I actually expect to happen here is it's actually going to be subtracting 8 from ESP, right? And it's just putting it in the annoying form, right? It's adding a negative, and this negative is represented as FFFFFF, right? But, and it is an immediate here. We got this little dollar sign, so it's an immediate. So it's sort of adding negative 8 to ESP. So if ESP right now is 3D0, and I subtract 8 from that, then I should have 3C8, right? Because I went lower. 3C8 plus 8 is going to be 3D0. So anyways, this turns out to be neither here nor there. Really doesn't matter, but just wanted to clarify this point. All right, so there we go. I did that. ESP is now had 8 subtracted from it, and now it's C8. And now I have 2 pushes, and I have a call to string not equal. Now, the thing is, string not equal is not... String not equal is not like one of the normal sort of like string compare functions. It's not like some C function or anything like that. It's not string compare. It looks to be just some comparison function they've implemented themselves, right? So we don't know anything about this inherently going into it. But what we probably want to do is we probably want to see what the parameters being passed into it are. Before we even go in and disassemble it or anything else, let's just step over these 2 things and see what these parameters are. Because we might have a notion that a function named string not equal is probably going to be taking strings to compare. So I could execute these two push instructions, or I could just say those are both going to go on the stack. Let's look at what they are, right? So first thing, we have something that looks like an address roughly in the range of our binary. We're going to take that address, and we're going to try to view it like a string. So how do we view like a string? Andrew. In GDB. I know, right? You can't learn GDB if you're a Windows person in like, a couple hours. So X for examine memory, and then / format specifier S. So S for string. X/S, and then I'm going to paste that address, and I'm going to see what's at that address. Okay, that's interesting. There's that public speaking is very easy string again. Saw that in the strings when we did the output. So what's that EAX? Well, EAX right now is set to this. It's 804B. It's again something roughly in the range of our binary. We're going to copy that X/S, put that address, and that's my input string. So at this point, I could go into strings not equal. I could see whether it's comparing them, what it's doing. But at this point, I think I have enough evidence to say that maybe the input string should be public speaking is very easy. So I'm going to quit back out. I'm going to give this as the input, and I'm going to see if I can get to phase 2 with this. All right, so I'm going to run, restart it. Restart from the beginning, yes. All right, info breakpoints. I still have my breakpoints from the previous run set. So I'm still going to break at main, and I'm going to break at phase 1. This time, I think I'm going to get past phase 1, so I'm going to go set a breakpoint at phase 2 as well. So how do I do that? Well, I'm broken at main right now. So I could, step down, and find the address of phase 2, but this is a nice thing, and it has symbols. So I'm going to do break phase 2. There we go. Have that breakpoint. Just going to run. I'm going to run until I get to phase 1, right? But before I get to phase 1, it's going to prompt me for the input. Continue. All right, I'm going to put in this input. Uh-oh. Hope it doesn't consider that return part of my input. Public speaking is very easy. I'm now broken at phase 1, and then I'm just going to go ahead and continue and see if I get to phase 2. Success! Sorry, I'm tired. I don't have enough gusto to really, shout success at you at this point. Phase 1 complete. That's the string for phase 1. Now it's up to you to find the string for phase 2, and 3, and 4, and 5, and 6. All right? So, give it some input. La, 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 la. And start tracing the assembly. Figure out how, just go into the assembly for phase 2 and figure out under what case will it just return out. Because if we look at the assembly for phase 2, well, we have a call to this read 6 numbers function. Well, that's a hint. We have a call to explode bomb. Maybe we don't want to call explode bomb. So let's figure out how we can jump equal to jump over that, right? So start working your way backward. Don't want to hit explode bomb. Gonna read 6 numbers, apparently. Now you have to figure out what the input needs to be for it, basically. So this is where take a break, do whatever, come back, spend as much time as this on you want as well. Ask me questions. I'm basically just going to wander around the rest of the day. If you have a question, don't understand why it's this way, that way. Again, remember from the thing, if you want to set disassembly flavor to Intel, if you want to just look at it in Intel, if you don't want to learn your AT&T syntax for now, you can do right? You can look at it in Intel if you want. But anyways, take a break, ask questions, whatever. Okay. And then Jeff said he fixed the right.